So, good afternoon, everybody, and welcome to the seminar Search for New Physics in Accelerators and the Cosmos. Today, we have Dr. Andrew L. Miller. So, let me read something about him. He is a postdoctoral researcher at the KEF and the Utrecht University, where he specializes in gravitational wave physics and dark matter detection. His research spans several key areas, including continuous gravitational waves, dark matter interaction with gravitational waves detectors, primordial black holes, and the study of stochastic gravitational wave background. He applied advanced data analysis in machine learning techniques to detect and analyze signals from phenomena such as neutron stars and black holes. So welcome and go ahead.
Thank you. Yeah, thanks for introducing me. Thank you for inviting me. Thanks for arranging everything. Yeah, I'll talk about just different ways that we can probe dark matter using gravitational waves. And essentially, I'll talk about two different things. One is particle dark matter. So this kind of dark matter would interact directly with the interferometers and give off a signal that's kind of like a gravitational wave, but it's not a gravitational wave. And then I'll talk about primordial black holes as gravitational wave candidates and also dark matter candidates. And so yeah, I just will talk about methods as well to search for these types of dark matter, as well as some constraints that we've been able to place on both dark matter, particle dark matter, and primordial black holes. So just to give you some background, so we're talking about using gravitational wave interferometers to search for dark matter. So these are essentially kilometer-long size instruments, Michelson-Morley interferometers, but much more advanced. And they're essentially designed to measure the displacement of test masses or mirrors in this frequency band, more or less. And so the precision of these instruments is very high. So they can measure displacements on the order of 10 to the minus 21 meters. And what they really actually measure is a strain, which is a change in the displacement, a change in the path length of the light that goes up and down each of these arms divided by the length of the interferometer. So ideally, you can get better sensitivity by making the interferometers longer, but this costs a lot of money. So the people have to devise different ways of essentially measuring the positions of these mirrors very precisely by reducing other sources of noise, like thermal noise or quantum noise, and many types of noise you can have. The detection principle is that anything essentially will cause a change in the length, anything that causes a change in the position of the mirrors on each of these arms will cause the light to travel different distances down each of the arms, and anything that does this can be read off as a signal, because the light will travel different lengths, and so there'll be an interference pattern that results back here. And so that's the principle. So the observable is this strain, this delta L over L, which is essentially a amplitude and a phase evolution over time. And so every kind of gravitational wave signal has a unique way that it changes the space-time around the mirrors. And so whether there are two black holes that are emerging, or it's two neutron stars that are inspiraling, or whether it's a stochastic background, there are unique ways in which they cause the space-time around the mirrors to change. And so then the question is then, can we search for these types of signals? And in particular, for this talk, I will focus on the exotica sources, so not the conventional black holes that emerge, but longer-lived signals that come from ultralight dark matter and primordial black holes. And the key question is, can we use interferometers to search for dark matter? And so I'll first talk about ultralight dark matter, and to give you some context for what ultralight means. So this ultralight essentially means 10 to the minus 14 EVs, 10 to the minus 13 EVs, something like that. And the observable is some kind of interaction with the standard model of this dark matter particle. And so essentially, when you have ultralight dark matter, this means that the occupation number of dark matter particles in any given volume of space is huge, which is given by this formula here. Essentially, which assumes that all of the dark matter energy density is composed by this ultralight particle dark matter. So that's what you see this ratio is in some given volume, which I think this is the de Broglie wavelength. And so you can see that there's a huge number of particles in any given volume of the de Broglie wavelength. And this means that since you have such a high number of particles, you can treat this huge number of particles as essentially a superposition of plane waves, where each of the plane waves has a particular velocity that's given by the Max-Boltzmann distribution centered around the virial velocity of dark matter, which is essentially the velocity at which the dark matter flows through the Earth. And this central velocity of the Max-Boltzmann distribution is around 220 kilometers per second. And so essentially all these particles give rise to a coherent wave with a finite coherence time, which is given by this formula here, which essentially tells you that the wave is essentially a coherent, so it's a sinusoid, when you observe up to about 10,000 seconds. But it depends on the mass of the dark matter particle. And this also implies that since you have a finite coherence time, you have a finite coherence length for the dark matter wave, which is about 10 to the 9 meters, which is much longer than the separation between earthbound detectors. And this means that so not only is the wave a sinusoid up to 10,000 seconds, but it's also coherent at different detectors, which means that the signal that you expect to find in all earthbound detectors will be correlated and will be at the same frequency, essentially the same part of this wave, and it'll have a very similar amplitude. So you're looking for essentially a sinusoidal signal that has a similar strength in all earthbound detectors. So really what you're looking for is a bump in the frequency domain, so that's kind of like for any given model of ultralight dark matter, this is what the signal will more or less look like. But I haven't explained, how the signal actually appears in the detector. This will come next. But these are general principles of how we expect the dark matter signal to behave in the detector. So this is just a picture that kind of gives you maybe more of a sense of what's going on. So really the interferometers are sitting in some kind of wind of dark matter. And so the signal is local. It's not coming from, some very far away place in the universe. It's coming from, from here. And so this has implications in terms of, so since we're essentially looking for something that looks like a correlated noise source, like essentially a frequency that you observe in all detectors to have a power that's a bit higher than the average. And so when we don't, and there's nothing fundamental about ultralight dark matter. I mean, it's just that the frequency range that we're sensitive to for ground-based interferometers implies a dark matter mass range that's ultralight. So if you think about future gravitational detectors that will be that will fly in space, so like LISA or some of the Chinese ones or Japanese ones, their frequency ranges are much lower that they're sensitive to, which means that the mass range of dark matter is also much lower. And so, again, nothing fundamental about this range. It's just that we can search for dark matter with interferometers, and so we do. And so in the likely case that we don't actually observe a dark matter a dark matter particle interacting with the detector, we put constraints on the coupling of dark matter to these ordinary standard model particles. But as I will try to explain to you in the coming slides, we don't actually assume any given model of dark matter when we do these kinds of searches. We just look for any kind of coincidence frequency across different detectors that's essentially a sinusoid, a monochromatic signal that's present in all detectors. And then when we get no results, we interpret this null result in terms of a particular dark matter model. And so this means that these searches for dark matter with interferometers are model independent in the sense that we don't have to assume a particular model for dark matter when we are doing searches. We just essentially have to assume this paradigm of like ultralight dark matter has a high occupation number, a finite coherence time, and a finite coherence length. And from that, we can search for any kind of dark matter that has some particular observable, which I will go into in the next slides. So I'll now talk about these observational signatures for different types of dark matter models. The first one I'll talk about is a scalar particle of dark matter. And this dilaton dark matter will couple with particular strengths to photons or electrons. And and so this coupling implies that there will be oscillations in the electron mass and also the Bohr radius of the atom. And so this means that the size of different interferometer components will change over time. And so like you can write down essentially a new fine structure constant that relates these coupling strengths to this new coupling constant. And this new coupling constant it varies with time because this dark matter particle is oscillatory. It has a particular frequency, and which is given by the mass of the dark matter particle. So the the electron mass and the fine structure constant are changing over time at a fixed frequency, which is given by the mass of the dark matter particle. And so practically this means that the mirrors and the interferometers, so these two end mirrors, as well as the beam splitter, they are changing over time. And this is a very complicated description of some part of the interferometer. But essentially, so the observable is that the beam splitter and the test masses are changing in size. And if in other words, that the light will traverse different paths on the surface of the beam splitter when it comes like back down the y arm and back down the x arm because of the oscillation of the fine structure constant of the electron mass. And so this difference in path length that results from the change in size of the beam splitter, the change in size of these mirrors, implies that you have a signal that can be read out at the photodiode, or it implies some interference pattern that you can measure. And so one way you can look for this type of scalar dilaton dark matter is looking at essentially the same data set that we use to look for gravitational waves, this kind of differential strain, where you look for difference in the path length that's caused by the gravitational wave, or in this case, that's caused by this kind of dark matter particle interacting. There's another way to actually look for the type of dark matter, which is not in the ordinary data, but it's actually one of the auxiliary channels. And because eventually what happens is that this change in size of an object is not limited to just the two end mirrors in the beam splitter. It's changing everyone's size. And so what you can do is you can essentially take a laser and shine it through some solid cavity and compare its frequency to a laser that you shine through a vacuum, And the dark matter signal, since it changes the size and the index of refraction of the solid cavity, it will modulate the frequency of the laser. And so you can also look for dark matter particles that interact with this with the detector in a different channel, which is supposed to be given by this circle here. This piece of the interferometer, I think, has a solid cavity, and then you compare the laser frequency in this cavity to one that's in vacuum, and you try to look for the change in frequency that you would observe in the laser frequency. But yeah, so there's different ways you can search for this type of dark matter, and this is very much a work in progress in the sense that this way is very new. This is maybe like a few months old, and where this way is a bit more established, like maybe 1 or 2 years, people have thought to do these kind of searches in the beam splitter for these type of dark matter particles. So there's a lot of auxiliary data channels in the interferometer. There's maybe like hundreds or even 1,000. So there's probably other ways that dark matter would leave some imprint on the interferometer. So there's just 2 examples of that. And so there's actually been a search that's been done for scalar dark matter interacting with the beam splitter, not in LIGO or in Virgo, but actually in GEO, which is a detector in Germany. And because originally if you recall this picture, the signal comes from this difference in path length of the beam splitter. So it doesn't actually matter how long the arms are. So because you get a lot of the signal that is coming from the difference in path length at the beam splitter. So for GEO only has, I think, 100-meter long arms. But since it has since a lot of the technology in LIGO is actually tested at GEO, the noise reduction techniques are actually quite sophisticated. And so you can actually get better constraints by just considering the beam splitter effect using GEO than you could in LIGO. And so there's a particular method that they use, which I won't go into detail because I don't think it makes sense at this moment, but it may make sense later. so I can explain it later. And so what you do is you essentially you do a search and you don't find something, and then you put these constraints on the scalar dark matter particle. And what's plotted here is this coupling constant of the electron of the dark matter to the electron, or the dark matter to the photon, as a function of the dark matter mass. And you can see that this work is in green here. So you can get very very stringent constraints compared to other experiments, which are these are different colors here, and also this horizontal line. And so this should indicate that we can actually place very stringent constraints on dark matter using an instrument that wasn't even designed for this purpose. And the reason that we are doing this in the first place is just because we can, and not because someone had a brilliant idea that they could do this. But there's nothing fundamental. Again, there's nothing fundamental about this frequency or mass range. It's just that we happen to be sensitive to it using ground-based interferometers. And I think that's all I want to say for now about that. Something else you can do is you can search for axions, and so the axions could interact with photons, and they would couple to these photons in the laser light itself in each of the interferometer cavities. And the observable is that the left and right circularly polarized lights will travel at different speeds depending on what the axion mass is, as well as what the strength of the coupling is of the axion to the photon. And this change in speed is given by this formula here, where the LR is plus minus, I think, or minus plus, I forget. And but this change in speed is affected by the coupling constant, by the amplitude of the axion field, which is fixed by the local dark matter energy density, and and oscillates over time with the axion mass. And so this is actually an interesting idea because many of the experiments that search for axions, they require that you use huge magnetic fields to convert axions to photons and then back to axions. And so in this way, we don't actually need to throw a huge magnetic field in the interferometer. We just know that the coupling will occur to photons, and thus the light speed will change. And so you don't need to worry about this Primakov effect. You don't have to deal with these like light shining through wall experiments. You don't need huge magnetic fields. And the only catch is that you need to add some additional polarization optics to actually measure the polarizations of the lights after it's shining up and down the interferometer. But that's fine. And actually in Kagra and the Japanese detector, they are adding these polarization detectors now. But this does not actually compromise any sensitivity to gravitational waves. So let me give you an example of what these kind of search for axions could do in the future. Here's a plot showing the coupling constant as a function of the axion mass and for different detectors. So essentially the purple one is this space-based detector, and the blue one is Kagra at its current sensitivity, and then the red is advanced LIGO, and then etc. And so you can see that these different curves they get better and better as you get more advanced in the detector era, and you can get to quite low frequencies, low axion masses in the future when you have like DISIGO or these like space-based detectors. And so yeah, this is something that's in the future that I think with Kagra at the design sensitivity, this blue curve will go down to about here at the low frequencies. But it's quite promising to search for axions in this way. And this kind of behavior here comes from some resonances that from the fact that the axion mass is like at the right frequency to resonate the cavity. And yeah, okay. And so another kind of dark matter that's not a scalar, but now is a vector, which is called the dark photon, which is a gauge boson that will interact weakly with neutrons and protons or whatever, and in materials. And just like the other types of dark matter, this will cause some oscillation in the material. And in this case, you can think about it as that this dark photon has an associated vector potential, this A mu, and this gives rise to an electric field, which then gives rise to a force. And that force is sinusoidal in time at a frequency that's fixed by the dark matter mass. And and the strength of which is fixed by the coupling strength of the dark photon to the protons or neutrons. And so this dark electric force oscillates the mirrors, and because there's a vector nature of this particle, the positions of the mirrors with respect to the incoming dark matter field, they matter. And so the 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 mirrors in the y arm will oscillate at the same frequency, but they'll oscillate at a different amount depending on where they are in this dark matter field. And so this will give rise to a differential strain. So since the mirrors are oscillating at with different amounts, although the same frequency, this gives rise to differential strain, and you can measure this. And so there are actually two ways in which the signal manifests. One is this kind of like spatial effect because of the mirrors of being in different places, and one also comes from the fact that it takes light a fixed amount of time to move from the input mirror to the end mirror, so to go 4 kilometers. And so within the time that it takes the light to move, 4 kilometers, the dark matter has interacted with the mirrors and has caused them to move a bit. And so you have an additional strain that comes, that's like a temporal effect that comes from this finite, the fact that it takes light a fixed amount of time to move between the two mirrors. And then finally you have, well, the last one I'll talk about anyway, is that you have a spin 2 particle that could interact with the detector as well. This is actually quite similar to gravity. So it kind of changes the space-time in such a way where you essentially have a coupling strength, which is this alpha. And again, you have this sinusoidal oscillation over time. And so this looks like a Yukawa-like fifth force modification to the gravitational potential. And so you can basically, again, you can run the same kind of searches that you are doing for the other particles, but then constrain these kinds of tensor bosons just using this equation here. And so yeah, there's just many ways that dark matter could couple, and these are certainly not an exhaustive list. I'm sure there are other ones that I'm not talking about, but this just gives you an idea of the breadth of sources that you could have that would couple, the breadth of dark matter that would couple. So now I'll talk about how we actually search for them, all these types of models. And so the idea is that your input is this time series strain, which is this h of t. So h of t versus time. And then you have the noise, which is this, this blue kind of Gaussian thing. And then you have your signal, which is much weaker, and it's this red thing. So the idea is like, how do you find a weak signal embedded in a strong noise? And the ideal technique to do this is called the match filter, where you have a model for what this red signal looks like, and you just correlate that model with the data, and you look for and if it's the right model, you will get a peak. You'll get a very high value of your detection statistic. It's kind of like trying to It's kind of like trying to find a particular voice in a crowded room. Like you kind of the voice that you're looking for, and you listen for that voice. The match filter is the same way. You know the model of the signal, and you look just for that one. This works when you know the model, but actually, in the case of this ultralight dark matter, you know the model, you know it's sinusoidal, but it's only sinusoidal up to its coherence time, because once you observe for longer than the coherence time, the waves, you start to actually be able to resolve the individual waves that make up this huge wave packet of 10 to the 54 particles. And so this is actually a stochastic fluctuation. And so you cannot actually use this match filter to search for these dark matter particles, because this match filter is deterministic. You need to know the model. You need to know exactly what the power is in the frequency domain. But so we have to devise other ways of doing it. But what we can do is, we know the signal is basically monochromatic, and so we can take Fourier transforms that are of length that are about equal to the coherence time, and then combine the power later. So in each of these chunks, we take a Fourier transform, and then we sum the power in each of these chunks. So in pictures, this means that you break the data into these smaller time chunks with T1, T2, T3. You take the Fourier transform, and then you create what's called a spectrogram. It's like a time frequency plot. And you can see at each of these times, the signal is monochromatic. And so you choose this duration such that the signal is monochromatic. And so in T1, T2, T3, or whatever, you see that where it's red, this is the where the signal frequency, where the frequency of the signal is. And in this plane, this time frequency plane, you sum the power at each time at every frequency. And this is more or less what you do. And so you lose sensitivity in this compared to this because you don't have the phase information. This is just power, but you are able to do the search because if you take a Fourier transform that's longer than this coherence time, then as I will show you in the next slide, you don't have the signal localized at one frequency. The signal is power is spread at multiple frequencies. So as a picture of that, this is a simulated dark matter signal for 1 day, but it's actually lasting, forever. This is strain versus time. And the coherence time of this signal is something like, I think, like 10,000 seconds or something like that. If you take a Fourier transform of this, naively, you get a frequency domain, a power versus frequency domain plot where you see that the structure. And ideally, you want the signal power to be at one frequency. You want all of this to be at one. Oh, sorry. You want all this to be at one frequency because you don't know the form of this. You don't know where the power is. This is a random thing. So it's stochastic. So, this may seem like a small amount. Like this is like a few millihertz, but when you're doing a search for 1 year, this really matters. That you have to be. You cannot hope to have a good sensitivity if you're summing signals that look like this because there's too much spread in the power here. And so yeah, this is like this kind of analysis strategy is that we're looking for a monochromatic signal. So we want to take Fourier transforms. That's like the best way to look for monochromatic signals. And we want to actually ensure they're monochromatic by fixing the Fourier transform length to be equal to the coherence time of dark matter. And then we sum the power at all these frequencies. And so one way you can do this is through cross correlation, which is exactly what it sounds like. You just take you essentially multiply the power from each detector together, and you divide by the noise. And so these are just some formulas that explain it, but I don't think they're that important. And I also don't think the information here is that important either. But the idea is that you do this cross correlation, and you look again at particular frequencies that have high values of the so-called signal to noise ratio, this SNR. And so the input is essentially Fourier transform of data set 1 times Fourier transform of data set 2. And you multiply, and that is essentially what your signal looks like. And then you estimate the noise in some way, which I won't go into how we do that. But you can essentially take a median or something like this to get the estimate of the noise. And the SNR is just essentially your signal just divided by your estimation of the noise. And you have high values of SNR, and this is every frequency bin. So if you have high values of the SNR, like 5 sigma or whatever, then you say, okay, I have something significant. I'm going to look more into detail with it. Okay, so that's cross correlation. The other method is you can make these time frequency plots like I was saying before, and you can really try to fix the Fourier transform time to be equal to the coherence time of the dark matter particle. And here is a time frequency map where the color corresponds to essentially the ratio of the signal power to the estimate of the noise. So essentially, if there's no signal, the ratio should always be 1. And this is essentially something like the number of standard deviations away from 1, or away from the noise. And I injected a fake signal here. This is what the dark matter signal will look like. It just looks like a line in the time frequency plane. So it's at one frequency. And then you can essentially just sum at every frequency the power, or in this case, we don't actually sum the power, we sum something like the power. And so this sum essentially corresponds to kind of creating a histogram. And so that's what you see here. You do this sum and you count the number of points that fall in each of these frequency bins. And that's what's plotted here as a function of frequency. And you can see that the signal is quite clear. It matches the frequency here. And you see a second one here. This is because the signal frequency actually falls between 2 frequency bins. this is a discretization problem. This is a very well-known problem in signal processing because you can never know exactly where the frequency of your signal is. It will never exactly be in a bin. And so you have this discretization problem. But it's not really a problem. It's just life is what it is. And so these are two methods that we use to look for this type of dark matter. Cross correlation is very similar. It's just that they use a particular FFT length, whereas in this method we can actually vary the FFT length based on what frequency that we're looking at. So we can be optimally sensitive to a particular dark matter mass. So just to give you an idea, like this coherence time can vary by an order of magnitude at the low frequencies versus the high frequencies, the low mass versus the high mass. So if you can tune the FFT length to be, equal to the coherence time, you can preserve the maximum sensitivity to this kind of interaction. So we did a search for this type of dark matter interacting with a detector, and using O3 LIGO data, which is the most recent publicly available data. And so we use these two methods, cross correlation and one based on this excess power. And we didn't find anything. So we put constraints on the coupling strength of the dark matter particle to the standard model ones. And that's plotted here, this coupling strength as a function of frequency or mass. And the different colors or different methods. So really the red and the blue is what you can look at for the searches with gravitational wave interferometers, and the purple and the green are from different experiments. They're constraints. So this is the coupling strength. So this is eventually normalized by the electromagnetic coupling strength. So this essentially means that the relative strength of the dark matter coupling to baryons versus the electromagnetic coupling is 1 part in 10 to the 42. So it's a really small fraction of the electromagnetic coupling. And so you can see that both of these searches are able to improve upon the limits from these other experiments by orders of magnitude, which is really, really good. And again, with an instrument that wasn't designed for this purpose, just one that is measuring precisely the positions of mirrors over time. There's also another search that was done using Kagra, where the detection principles also is very similar. It's just that it's not, as I mentioned before, it's not always the best way to look for these type of signals in the differential arm length. There's other data sets, other channels where the signal could actually appear to be stronger. And in the case of Kagra, this is the case for these dark photons. And these two different ways that you can combine the measurements of the lengths of the cavities, you actually find they're a bit more sensitive. And so the other thing is that for this, especially not for when dark photons couple to baryons, we have constrained this here. But if dark photons couple to baryon minus lepton number, then the difference in charge between different mirrors in the interferometer can actually give you an enhancement of the strength of the signal. And so in Kagra, I think the materials of the mirrors are like sapphire and I don't remember the other one. Maybe it's on the other slide. Sapphire and maybe use silica. And this means that you actually get an enhancement that's proportional to the difference in the charge to mass ratio of these two materials. And so this is very good. So you can actually, by picking different materials for your mirrors, you can improve your sensitivity to types of dark matter that couple to baryon minus lepton number. And this is just an example of this. So these are constraints on the same coupling constant, but the square root of what I showed you before for the different data sets. So you can see that they're really messy. And this is because these data sets are not clean. People don't care about them. So they're not really used for observational science. And so we have to do a lot of work to really improve them. But this is the first search that we've been able to do. And also, just to give you an idea of the future of these kind of searches. So this is, again, this coupling to baryon minus lepton number as a function of the dark matter mass. And each of the colors corresponds to different channels of the interferometer for Kagra. And so you can see the blue one is the strain, like the one I've been talking mostly about. But these red and green ones are these Michelson and Perkel, these different data sets that come from the interferometer. And so you can see that there's much stronger constraints, especially at low mass, using the data from these channels. And these channels are basically just clever ways of combining the difference in lengths between different objects in the interferometer. So I think Lx and Ly are just the difference between the beam splitter and the input test mass mirrors. And so I mean, there's nothing, I don't think it's intuitive to understand like why these channels are better especially at low frequencies. So it's something that has to really be tested, and you have to actually write down what the noise sources are at these low frequencies, and compare what the strength of the signal will be in those channels compared to the ordinary strain one. So I mentioned briefly before that you can also look for this type of dark matter at low frequencies in space when these detectors fly. So we did a very let's check the time. Oh, I should really wrap up. So what time did I start? What time did we start? At 10. At 2:10. Oh, okay. Maybe 10 more minutes I can talk for. And so we can also search in space for this type of dark matter particles. So the signal is essentially the same. It's just that the frequency range has shifted to a much lower frequency because LISA and other space-based detectors will be sensitive to like millihertz gravitational waves. And so you can do the same kind of searches using the same techniques. And so we showed that you could do this with LISA Pathfinder data, which was some kind of like precursor to LISA. And but the problem is, well, there are many problems with this data. But one is the fact that the arms are so short. Like I think it's 30 centimeters or something. So you don't get a lot of strain from the passing dark matter wave. But also it's only one arm. So part of the reason why there are two arms is to cancel the laser frequency noise. And so since you only have one arm, you have no cancellation of the laser frequency noise. And so the coupling strength squared is a few orders of magnitude, or probably like 10 orders of magnitude higher than what we obtained using the ground-based detector data. And that isn't expected, it's fine. But it was a proof of concept method. But there is a particular mass range that you can exploit, that you can actually obtain sensitivity, like realistic sensitivity to this coupling strength, again by using this principle of the different materials of things causing like an enhanced strength of the signal because they're different charge to mass ratios. So in this search, we just looked at the two test masses, the difference in length between them. But in this mass range, you can actually look at the difference in length between the spacecraft, which is one material, and the test mass, which is different material. And just as in the case of Kagra before, the different materials of the input mirror and the beam splitter, the fact that the spacecraft is, I think it's made of gold, and then the mirror, which I think is fused silica or something, this gives you an enhancement of the coupling of dark matter particles to the baryon mass lepton number. And this means that you can actually probe a physically relevant coupling strength in this mass regime. But again, nothing is intuitive about this. You have to actually work it out. It's not doesn't really follow from fundamental principles. Okay, in the time I have left, which I guess is like 10 minutes, I will just talk about gravitational waves from primordial black holes. But very generally, I won't go into too many details. So essentially you have this picture of what primordial black hole masses could be. So they could basically range from 10 to minus 18 solar masses up to 1,000. And this is because just like dark matter, we have no reason to prefer one mass over another. And so essentially after the first detection of black holes merging by LIGO and Virgo, the low spins and the inferences for the merging rates that were made are consistent with primordial black holes or PBHs, and this was this revived the interest in primordial black holes as a dark matter candidate. And so you can see different constraints that come here. This on the y-axis is the fraction of dark matter that primordial black holes could compose. And this is essentially the quantity that you constrain in these types of searches. And so these different colors correspond to different experiments that were designed to look for primordial black holes, but they all have different assumptions that go into them. So there are assumptions about what the distribution of the masses are of primordial black holes. There are assumptions about whether they form binaries. There are assumptions about how they formed in the first place. So these are all baked into these different curves. So you really have to be careful with how you interpret them. But so just to be aware. And from the gravitational wave side, people have focused mostly on black holes that are essentially at 0.1 solar masses or above, so between 0.1 and 1. And you can get pretty good constraints on this fraction of dark matter. And the reason to care about subsolar mass black holes is because we don't have ways of producing them in any kind of stellar evolution model. So if there are actually black holes at these lower than 1 solar mass range, then they are probably primordial. At least we can't think of ways they could have formed astrophysically. And so but there's a large mass range, this one that really hadn't been searched for before recently. And the reason is because like the techniques that are used to find black holes that merge with LIGO and Virgo, they are based on this match filter, this deterministic technique. And you need many, many templates that you correlate with the data. And so this is really computationally intensive. And so when you have these low mass black holes, you have longer templates, which means that when you space them, like when you do the search, you can't just like randomly throw down, templates, 1 solar mass merging with 2 solar masses or 3 with 4. You have to place them in a very specific way. And this bank of templates, or template bank we call them, is very, very dense when you have such long lasting signals, which is what happens for these lower mass systems. So the lower the mass, the longer it takes the systems to inspiral. And the longer it takes them to inspiral, the more phase mismatch accumulates between different templates. And so you need more templates to cover the same parameter space as you would for the higher mass systems. And to give you an idea, this is a plot that shows you the duration of the inspiral of different black hole systems as a function of the frequency at which you observe them and the Chert mass. And the Chert mass ranges from 10⁻⁷ to 1. And the Chert mass is just this weird combination of masses. This is actually the observable. This is what enters into the phase evolution of the signal. And so you can see quite a range here, from longer than the age of the universe at these low Chert masses to, hundreds of seconds at the high Chert masses. So essentially, the range off of the plot at higher masses is covered by LIGO black hole searches now. And the subsolar ones I just talked about, they basically end here. And so we want to actually be able to probe this mass regime, which is basically from this entire block here. And so I will just tell you that the signal looks like this. It has an associated frequency drift over time, which is based on the Chert mass. And again, with these kind of searches, we are thinking about doing them in the time frequency plane. So what matters is how does the signal look? How is the frequency versus time evolution of the signal? So the integral of this is what matters. And so you can integrate this, you get a track in the time frequency plane, and you search for that track. And in pictures, I can show you what this means. So this is an example of a time frequency map like I showed you before. And this is the red line here is a simulated inspiral of 2 primordial black holes, and lasting for like 1,000 seconds and spanning 40 hertz. And so basically what we try to do is we know that every combination of masses, M1, M2, gives rise to a different track in this time frequency plane. So we essentially place different templates. We sum the power across different tracks, where each track corresponds to a particular Chert mass and a particular reference frequency. And we histogram them in another plane, which is given by the Chert mass versus the frequency here. This is actually something called the Hopf transform. And so you essentially are summing the power along different tracks, and you're histogramming that power or something like the power in this plane here. And where the color is something that relates to the signal power. And so and again, each track is unique. So each track on this plane corresponds to one pixel in this plane. And so you can see that when you guess the right track, you see that a particular pixel is lit up, which corresponds to exactly the parameters that describe this curve. And I won't go into this detail. We did a search and we didn't find anything. And we found some candidates, but they were all thrown out. And I won't go into this either. And I'll just explain that when we do these searches, we again constrain something so we don't find anything. And so what the observable again is strain. It's not really like the fraction of dark matter that primordial black holes could compose. This is just the interpretation. And so what we actually have is a strain as a function of frequency that we obtain from the data. And from this, we can actually convert this into a distance reach using a formula. And this is you can find this in any textbook. And then this distance reach allows us to compute like a volume away from us that we're sensitive to. And when we have a volume and we have our observing time, how long we observe for, we can compute a rate, like a rate density. So the number of sources we didn't find per volume per time. And that's what's given by this quantity here. And then we can interpret this rate as arising from primordial black holes. And when you do that, then you have some expression that you can obtain from primordial black hole formation models that relates the expected rate density to the masses of the primordial black holes, as well as the fraction of dark matter that primordial black holes could compose, and also what you assume that the mass function of the primordial black holes is. So typically when we put constraints, we assume that at every given mass that all of the primordial black holes would be at that mass. This is not a good assumption, but this is what we do. And so like this kind of like trajectory. So you start with strain, you get distance, you get a rate, then you equate this rate density to essentially what you get from theory. This allows us to constrain the primordial black holes. But up until here, there's no indication that we're looking at primordial black holes. We're just doing searches for two compact objects with masses below 0.1 solar masses. And so I'll just quickly say that we are able to constrain pretty well the asymmetric mass ratio systems. And here is this distance reach as a function of the secondary mass or the Chert mass. And also the rate density constraint is given here. And so everything above this line is essentially excluded. And it's independent of what you assume for primordial black holes, or if you just these masses these distance away cannot exist, that we would have seen them. And if you want to then invoke some model for how primordial black holes form, then you get a more complicated plot where you can constrain this fraction of dark matter that primordial black holes could compose, or you can play around with the constraints and constrain the mass function of the secondary objects. And you have a lot of freedom here. You're not like this is just one plot you can make, but you have the freedom to choose. I can go back. You have the freedom to choose M1 and M2 to be whatever you want, because the observable is the Chert mass. And so different combinations of M1 and M2 will give rise to the same Chert mass. So you are free to constrain whatever you want with these kind of searches. And so as long as they follow this particular signal model, which I gave before. But yeah, so just I want to conclude by saying that yeah, there are many ways you can probe dark matter with the interferometers, both particle dark matter as well as gravitational waves that come from some dark matter source like primordial black holes. And also in the future, like space-based detectors will provide even more interesting probes of different mass regimes of particle dark matter. And if you're interested in working on anything, you can please send me an email, or if you have questions you don't feel like asking in front of people, you can always write me. So thank you very much for your time.
Let's go for some questions.
Photons in some way. So with these experiments, it is possible to detect the signals of gravitational waves coming directly from dark matter, even if it is not coupled to photons.
Yeah, so do you mean, so if the dark matter couples to photons, it gives rise to like a particular signal, and it's independent of the gravitational waves. So I think you're referring to, let's go back. So you mean like the axions coupling to the photons, or you mean? Yeah, here, yeah.
So it generates a signal of gravitational waves.
So I think this if the dark matter doesn't couple to materials, like if this is the wrong model, then it will not generate gravitational waves. Because the gravitational waves are generated by the changing space-time. So they are independent things. So like if this scalar element doesn't exist, then the materials won't change in size. And so the only stuff that you will read out will come from black holes that merge or from other sources of gravitational waves.
But what
Hmm.
are generated by dark matter, you know, as a scattering from a scattering process.
Oh, a scattering process.
Yeah.
I don't know. I guess it's possible. I know that there has been some work that has considered like macroscopic dark matter that will scatter off of um the different components and give rise to like a gravitational wave-like signal. But I don't think that the signal will be that strong that uh, if the particles exist, but they're not coupling to dark photons, there's only specific ways in which it would create a gravitational wave. So like if the particles, for example, form around black holes, they will superradiant. There'll be some superradiant process, and they will give off a gravitational wave. But what you describe, I don't think it would give off gravitational waves.
Maybe because this is at low energies, isn't it?
It's a low energies, yeah.
But I guess, or I wonder if the charge would have some, value.
Yeah, I think it's possible that there could be problems. But I'm not aware of like what the implications of that would be. So yeah,
Thank you.
not a problem.
Anybody else?
Hi.
Hi.
You show the different models, for example, scalar or dark photon.
Mhm.
But what's the difference in the detectors? Because I don't see, or so I didn't understand how did how you uh, how can you compute the observables in
Uh,
interferometers?
yeah, I mean, there's only really one observable, which is the strain. So like the difference in this case, this type of scalar dilaton dark matter, if you're looking for this effect on the beam splitter, and in the case of the dark photons, if you're looking for this effect on the mirrors, a priori you will not know what you're seeing, because you only have the strain as the observable. And so when we compute the limits, we are assuming one of these models. The only thing I can think of is that you can if you, for example, find this dark matter in a different channel of data of the interferometer, then you can be sure that it's this one and not the dark photon. But there are also things you can do, like you can use something called you can look for like each of the types of particle dark matter will have a little bit different power spectra, and especially their cross power will be different. So the multiplication of the power of the Fourier transform of like detector 1 times detector 2 data, this power spectrum will be different for different types of dark matter. So you can look at the cross power to distinguish between what types of dark matter that you're seeing. So I guess that's probably the most robust way of doing it, to actually be able to distinguish, assuming that you're looking for this type of dark matter and also the dark photons in the same data set. I think that's what you would have to do. But in the search itself, the one that we actually do, we don't assume we know what we're looking for. We just look for something and then we assume a model to constrain. But the observables are different. I mean, this changes the beam splitter, the dark photons change the beam splitter. The dark photons change the mirrors. So there is actually the observable is different, but the data that you get is the same. So yeah, it needs other ways of distinguishing.
Thank you.
Let me see if maybe online there's.
In the meantime, I have a naive question.
Yeah.
What is the difference between extra dark matter and dark photon?
I think dark photon is just like one type of vector. Like it's this, like this dark photon assumes that it couples to the protons and neutrons, but then there are dark photons that are like kinetically mixed, which I don't really know what that means, but the coupling is different. But I think dark photon is just like one type of vector of dark matter. But I'm not a theorist, so I don't know if there's other kinds of dark matter that they look
Right,
for.
I mean, you expect different signals from each.
Yes, each model will give rise to a different signal. Will couple to a different particle and therefore have a different observable.
I can find any other question.